All right, guys, welcome back to the channel. Right, thank you guys for watching. Thank you guys for subscribing. Really like the help. This video is part of a playlist that I'm going to be doing on trigonometry. Now, in this video, what we're going to be doing is we're going to be proving the sum and difference identities. Right now, to do that, we're going to take a triangle from the unit circle. And why we're taking it from the unit circle is because we want the hypotenuse to be equal to 1. So I'm just going to draw a small half a circle up here and a nice little triangle inside that. All right. Now recall that if we're going in the x direction, that's the cosine of alpha or theta, sorry. And if we're going in the y direction, that's the sine of theta. So theta would be here, and we know that the hypotenuse is 1, right? And that's just for you guys to get a look at the triangle that we're going to be taking from the unit circle. So I'm going to draw that triangle inside a rectangle that we have right here, because this is a nice little geometric proof, right? That's why we're using shapes. So let's get a nice little rectangle over on this side. There we go. Not drawn to scale, but that's fine. And we're going to take that triangle, right? It's going to be a little bit bigger. It's going to be a little bit bigger here. But I just needed you to see that the hypotenuse of that triangle is going to be 1, right? And we're going to put that right triangle inside of this rectangle. But we're going to turn it slantly like that, oblique. So we're going to create that triangle from the unit circle. We're going to put it right here. There we go. Might not drawn to scale, but we want that little corner right there to be 90 degrees. All right. So again, this angle right here is theta. That doesn't change. That's theta, right? And the length of this hypotenuse right here is 1. Just want to make that very clear. Now, we're going to get the angles, the different angles of these parts, because we need that. We know that this is a right angle triangle, a right angle triangle. So we can see 1, 2, 3, 4 triangles right here that we're going to be using to prove the sum and difference identity. That's the fact that the sine of theta plus alpha and the cosine of theta plus alpha. This is what we want to prove, right? We know that this would be equal to the sine of theta cosine alpha plus sine of, I need more space. Let's remove that because I think we already used that circle, plus the sine of alpha cosine of theta. And for the cosine, it's going to be cosine theta cosine alpha minus sine theta sine alpha. That's what we want to prove using this rectangle right here. Now, to get the sum of the angle, we're going to look at this angle down here that forms this right angle triangle. Let's write that 90 degrees a little bit better. Right? And we're going to call this angle alpha. Right? So this angle right here is alpha. There's a lot of properties that we're going to be using. So I really want you to pay attention. Just listen, right? And if you don't get it on the first try, you can go ahead and rewatch the video. It will always be there for you. Now, notice that the properties of the rectangle is that opposite sides are equal in length and opposite sides are also parallel, right? So if we know that opposite sides are parallel, recall that parallel lines, if we have a slant line like that, cutting a pair of parallel lines, we call that a transversal line, right? And if the transversal line cuts two pair of parallel lines, we get some nice angles, right? Like alternative angles, corresponding angles, and all of that. So if you look at this parallel line, let me just extend this side out and extend this side out. So you can see the parallel lines like that. And let me just extend this side out and this side out like that. right? So you can see that this angle right here, right? This angle is alternately equal to this angle right here. Are we seeing that? So this entire angle, which is theta plus alpha, this angle is also equal to theta plus alpha. So we're going to have theta plus alpha right there. Now, another nice little property of triangles, right, that we know is that the exterior angle of the triangle is equal to the sum of the opposite interior angles. We know that if we have a triangle, for example, like this, right? Just saying, and we could have extended the vertex of any side. And these two sides right here, this angle and this angle, will be equal to this external angle right here, right? So we know that this angle plus this angle is equal to this angle right here. And I want you to pay attention closely. And look at this right triangle down below. Like this side is the hypotenuse right here. We're looking at this right triangle. Now, the exterior angle, which is this piece right here, let's put a dotted piece around that. That exterior angle is equal to the sum of these two opposite interior angles. And this is 90 degrees plus alpha. Well, we already have 90 degrees here, which means that this angle right here is alpha. So we're going to put an alpha right here. Now, what we need to get in is some of the dimension of the other two dimension of this triangle that we took from the unit circle. Remember, if this is a triangle that we took from the unit circle, this side right here, which is the hypotenuse of this lower triangle right here, is going in the x direction, which is the cosine of alpha, of theta, sorry. So it's the cosine of theta. And then this side would be the vertical side inside the unit circle, and that's going in the y direction, sorry. So we say that that's the sine of theta. So we got that in terms of sine and cosine. What we need to do now is to get the dimensions of the rectangle in terms of sine and cosine. So we're just going to use trigonometric ratio properties that we know to get to that. Let me remove these extended pieces so that you can clearly see where we're about to get at. Now, let us go. We're going to use the ratios, the trigonometric ratios, to get the dimensions of the sides of the rectangle. Starting with this upper right triangle right here, this one right here, where this angle here is alpha plus theta, and the hypotenuse is 1. So this is the opposite side of this angle, right? So the sine of this angle, so the sine of theta plus alpha is equal to the opposite side. We don't know what this side is equal to. Let's use a letter. Let's say z. It's equal to z over what? 1. But if we are going to write this side in terms of sine or cosine or sine and cosine, we need to know that, hey, z over 1 is the same as z. So z is equal to the sine of theta plus alpha, right? So on this side right here, we're going to replace z with the sine of theta plus alpha, right? Wrote that in purple. So we got one side down. We got 3 more sides to go. Let's go. If we look at this side down here, this length, this is a nice little one. This is the opposite side. This is the adjacent side, right? So if we need to find the adjacent side, let's focus on this lower right triangle right here, where cosine of theta is the hypotenuse, right? So if we need to get the length of this side in terms of cosine or sine and cosine, we need to take in relation this angle alpha. Now the cosine of alpha is equal to the adjacent side. Let's name this adjacent side t, right? Just saying. So the cosine of alpha is equal to t over the cosine of theta, because the cosine of theta is the hypotenuse, right? But we need t. We need to transpose to make t the subject. So we're going to multiply both sides by the cosine of theta. What do we get? The cosine of theta times the cosine of alpha is equal to t. So we're going to replace t here with the cosine of theta cosine of alpha. There we go. Now we have two more sides to go. Two more dimensions. Let's go. All right, we need to know the length of this side right here. But now, pay attention. This side is part into two pieces. We got this piece down here and this piece down here. So we got to do them in sections. So we're going to focus on this piece down here first. We're going to focus on this length from this point to this point, right? So we need to know what that length in terms of sine, cosine, or sine and cosine. Now this is the opposite side to alpha, this lower right triangle, the opposite side. So the sine of alpha, that's this angle, is equal to opposite. We don't know what that side is. Let's use a variable to represent that side. Let's say that side is b, right? The sine of alpha is equal to b over the cosine of theta. So as you can see, if we need to get to b, we're going to multiply both sides by the cosine of theta. And we have that b is equal to, because this cancels out, b is equal to the cosine of theta sine of alpha. And that's just from this piece to this piece. So we're going to move that and we're going to put a nice little curly bracket like that. And we're going to say that's equal to cosine of theta cosine of alpha. We're getting there. This piece right here, we're going to use this upper right triangle in the top right corner. You see that little small triangle with reference to this angle, alpha, to get to this side. So this side here, where sine of theta would be the hypotenuse of this upper right triangle. Now, to get to this side, it's adjacent to the angle theta. So angle alpha, sorry. So it means that to get to that angle, we need to take the cosine of this angle right here, alpha, is equal to, we don't know this side. Let's use another same variable. Say it's equal to f, right? It's equal to f over the hypotenuse, which is the sine of theta. So in reality, if we multiply both sides by the sine of theta, we get f is equal to, because these cancels out, f is equal to the sine of theta, the cosine of alpha. So f right here is equal to this piece. Let's get a different color for that piece right there. Let's use green. This piece right here, from this point to this point, is equal to the sine of theta cosine of alpha. And we only have this piece up here left to go. Let's remove that piece. We also need this little piece right here, because notice this length right here is also split into two pieces, this portion and this portion right here. So we need to calculate or get the distance of this point to this point in terms of sine or cosine. Let's see what that is equal to. Now, in relation to this upper right, we're still in this upper right triangle. This angle right here is opposite to this side. So the sine of this angle, alpha, the sine of alpha is equal to the opposite side. We don't know what that side is. Let's name it a variable w. It's equal to w over sine of theta. And again, transposing make w, the subject, we multiply both sides by sine of theta. So it means that w, because these cancels out, w is equal to the sine of theta sine of alpha. So we can replace that with the sine of theta sine of alpha. And that's from this point to this point. This point to this point. We need to know what's this point to this point. Now, this point to this point, we're going to use the upper left right triangle, this big one right here, in relation to the angle here of alpha plus theta. Now, this is the adjacent side, so it means that we're going to take the cosine of that entire angle. So it's the cosine of theta plus alpha is equal to the adjacent side. We don't know what that side is. Let's give it a variable. We're going to name it x. All right? X over, so it's the adjacent over the hypotenuse, which is 1, So it means that x is just equal to the cosine of theta plus alpha. So we're going to replace that with the cosine of theta, just write that properly, theta plus alpha. And that's from this point to this point right there. So now that we have the dimensions of the rectangle, again, the properties of the rectangle is that opposite sides are equal in length. So if that is true, it means that, let's go here. Let's take the red. This is what we're going to prove. Let's start with this one, the easiest one. This side is equal to this side. This side is sine of theta cosine alpha plus cosine theta cosine alpha. So it means that the sine of theta plus alpha, which is this side, is equal to the length of this side, which is equal to this plus this. It's the sine of theta cosine of alpha plus the cosine of theta. Wait, why do we have cosine right here? Opposite over the hypotenuse, it should be a sine of alpha. I made that mistake so long ago. Not doing this video again, guys. So, bear with me. Sine of alpha. Right, would have gotten the picture, but that would be a sine because remember, in relation to this angle, this is the opposite side over the hypotenuse. So it's the sine of this angle here is equal to this side over the hypotenuse. So it should be a cosine sine. And I know that because then it could be cosine here, because that would be for the cosine of the angle, the sum of the angles, right? So we clarify that, right? Probably get in the comments way before I corrected this, but that's fine. Anyways, let's move on. Right here, we are going to the cosine of theta plus alpha. This is what we need, the length of this side right here, from this point to this point. But remember, this side is equal to the length of this side, right? So if we need only this piece right here, the cosine of theta plus alpha, it's going to equal to the cosine of theta cosine of alpha minus this piece right here. So the cosine of alpha plus theta, or theta plus alpha, whichever way, is equal to this length right here, which is the cosine of theta cosine of alpha. And we're subtracting this piece because we only need this. We only need this, right? So we're subtracting the sine of theta and the sine of alpha. And there you have it. The proof, the geometric proof of the sum of the angles. Now, to get to the difference of the angles, all we have to do is to get to some other identities that says that the sine of negative theta is equal to the negative sine of theta, right? And I can quickly show you that. We're going to show you that in the next video. So we can use that to prove the difference of these angles. All right. Thank you guys for watching. I hope you really enjoyed. I'll see you in the next video.